Hello, everyone. This is lecture 28 of Petroleum Reservoir Geomechanics 465. We should be starting the last module here today, module 4, wellbore stability, which is a pretty, it's a significant module, and I see it as a transition from the theoretical stuff of geomechanics to the more applied stuff that we will start doing. We will really get into that in 475, the class that follows this, which is much more applied. 475 for undergrads, 575 for graduate students. I think for graduates it's called advanced stimulation techniques. For undergrads it's called well completions. And this is basically a more applied version of what we learned in this class. We will talk about, basically we have the REV that we started talking about from the first module. We talk about the in situ stresses, externally applied. Then we talked about interrelationships between stress and deformation behavior. We did it in module 2. Then module 3, we talk about failure criteria and rock failure analysis in general. And we mostly focus on shear failure because we had seen tensile failure at the module 1. And now we're gonna put a well inside the continuum that we are modeling and see how does that change stuff. Because this class is really it's a geomechanics class. It's a geomechanics class for petroleum engineers. And petroleum engineers, they do wells, right? They drill wells and try to produce fluids from it, try to inject fluids in it. So petroleum engineers really care about geomechanics near the wellbore, in the near wellbore vicinity mostly. So if I could rename this class, which I wasn't the one who named it, Petroleum and Reservoir Geomechanics, I would have maybe named it near wellbore geomechanics or something. Maybe reservoir and near wellbore geomechanics, something like that. Because it's, you will see that when you drill a well, you remove rock and you replace that with fluid. And it creates what we call impediments, stress impediments in the near wellbore vicinity. So when you go to the near wellbore vicinity, you are no longer going to have SV, SH max, SH min. You have a different kind of stresses, a stress regime near the wellbore. In fact, you have stresses in cylindrical coordinates. You have axial stress, you have radial stress, and you have tangential stress. And when you want to see, you want to model fractures initiating from those points, you really need to use those stresses. So the stuff that we are talking about in the end of module 1, when we said, okay, the fracture starts, the tensile fracture opens against sigma 3. We said sigma 3. I didn't want to say sigma H min, sigma V, or SH min, or S. That's because you may not have sigma 3 may be a different stress in different places. Now, when you are near the wellbore, I want to know what is the sigma 3 at that point where the well is, the fracture is, I'm expecting it to start. So if I'm starting a fracture from a wellbore, I need to know right on the wellbore wall, what is my sigma 3? So it becomes a little bit more complicated in this way. I'm dealing with a different kind of stresses. And to make things even more complicated or even less complicated, you can see it this way, these near wellbore stresses don't depend on SV, SH max, and SH min. So when we take the far field stresses, which is basically what we talk about as SH max, SH min. Those are as if you don't have a wellbore there. Then you put a wellbore there, and you start looking at the cylindrical stresses, the DR wellbore stresses, and to calculate those, you need to use SH max, SH min. So they do depend with each. One affects the other in different ways. Before I started recording, there was a question on the homework. I want to address it before I start. I want the answer of critical pore pressure in the PSI per foot, but there is a catch here. In the example that we did in class, we assume SV is 1 PSI per foot. In your homework, it's not. So many times in the class, I was dividing by 1. No, I'm not dividing by 1. I think I'm dividing by 1.1, if I'm not mistaken. So be careful, that will change numbers. I want to make clear that, and thank you for Justin for pointing this out. So let's start with module 4. So that's what I have been talking about. This is from Zobak's book. And if you see, it makes a good example here, a good, not example, a nice schematic from 2007, if not earlier. Actually, I think this is from a 1985 paper by Zobak. If you see, I make a wellbore, I disturb the stress field around it. So I had a grid that was perfectly Cartesian. It was perfectly rectangular or square. And then I made the wellbore. Look at how I distorted the field. I make the lines get closer together here at the bottom and top near the blue arrows. And I push the lines away from each other by the red arrows on the left and right. So if you think about it, where the lines get closer together, I get a higher stress. And when the lines get far away from each other, they get lower stress. If I'm not mistaken, we are going to see that later on in more detail, of course. But this is how you disturb the field. Excuse me. And people doing research on tunnels in civil engineering and in my research on tunnel intersections, this is exactly what I was looking at pretty much. For well bores, it's a little bit more complicated because in real life in tunnels are empty. Well bores, they have fluid, they have well bore pressure, so you need to worry about this stuff. Okay, so the presence of the borehole, excuse me, disturbs the stress field in its vicinity, what we call the near wellbore region or near wellbore vicinity. I think we explained that. And then, because of the shape of a well, it doesn't make sense for me to use a Cartesian coordinate system. I have to use a cylindrical coordinate system. And look at, I made a mistake here. I have a mistake in the slides here. So this should be, no, it doesn't enable editing. So this should go here. And then this should go here. My apologies. That's the second time I'm teaching this class and I just noticed it. But anyway, I don't want to use a Cartesian system, which is X, Y, and Z. Because of the shape of the wellbore, to make it easy on me, I will use a cylindrical system or a polar system, R, theta, and Z. And if you remember, okay, let's see. From your calculus classes, I will use the a black pen to denote it. There is a reason for that. I don't want to use a different color because I have colors dedicated to different stresses. So I take the middle of the well and I imagine an axis going towards its side. This is the R axis, okay? That's the radial axis. And then I imagine another axis going clockwise. That would be the theta axis to another R, basically. And then another axis is the Z axis. Imagine an axis going into the screen or out of the screen. That's the Z axis. Okay? So these are the axes I'm dealing with now in the cylindrical coordinate. I'm no longer dealing with X, Y, and Z. There is a way to go from from polar coordinates, from cylindrical coordinates to Cartesian coordinates and back. But I don't want to have to go through that because this is an applied topic. I want to be able to calculate the stresses I want to as they are. So I'm gonna use this kind of coordinates. So the stresses I'm gonna deal with are the following. Radial, which I use green for it, since I was a PhD student, and is denoted by sigma RR. Tangential, which I use red, and is denoted by sigma theta theta. Axial, which is I use blue, and it's denoted by sigma ZZ, and sigma R theta is the shear stress. We are gonna use sigma R theta. Some people use tau R theta, some people use different stuff. Okay, so these are the four stresses I'm gonna deal with. Some people, they use the word hoop stress, HOOP. Yeah, they mean the red, the tangential stress. So some people call it circumferential stress. You will see why when I draw them. But if you hear circumferential, hoop, tangential, we all mean sigma theta theta. Okay? Then, how do we draw them? That's an important topic. And I will try to draw them. Let's just do it. Okay. I have, by the way, very, very important to know their direction. Very, very important. Okay. I have this. I go to the center of the well, and I draw an arrow. Oops, sorry. Won't let me. I draw an arrow and I intercept the borehole walls. Now, if I go to this arrow and I extend it, I will use green. If I extend it, this is the direction of sigma RR. That's the radial stress. This is the direction of a radius from the center of the well, extension of that. That's how I get the radial. Then I go tangentially to the radial at right angles and make arrows here. This is my tangential stress, my hoop stress, my circumferential stress. And then I have the axial stress, which is very easy. Is in the direction of sigma ZZ. Yeah, it's inside the perpendicular to the plane of the screen. So inside, imagine it going inside the screen. Now, you should be asking, where is the tangential stress? The shear stress, sorry. And for this, it's a little bit more complicated. You need to create an element. And REV is this location that we are looking. So I'm looking at the stresses at this location here on the screen where I drew them. Okay. But it's near the wellbore. It still has an influence by the presence of the wellbore. So it won't be a perfect cube like I have here. It will be something that looks like this. A disturbed cube. And if I want to draw the shear stress, let me use pink or purple. I think it's purple. Magenta. It would be like this. It's a shear stress, so it would be like this. Remember, the arrows meaning one edge and another edge. They are always sort of like maybe up here and maybe down here. And there is another issue here. Okay, the way I drew those stresses, they show the positive direction, the compressive direction, sorry, the positive direction for solid mechanics, which is the compressive direction. But in our work, in the subsurface, most of the times, it's compression that you have. Oh, sorry, I meant to say tensile. So for a solid mechanics class, they draw them like this because this is the tensile, and this is positive for them. But for us, most of them would be compressive. So it would be something like, they should look like something like this. Let's draw them down here. Let's draw them in this direction here. So I have the radial stress. Now it's gonna look like this. Sigma RR. I have the tangential stress. Now it's gonna look like this. And I have the axial stress. Gonna look like this. This is a more accurate. Yeah. By the way, I forgot to draw it, right? Sigma ZZ. And sigma RR, sigma theta theta. Okay. So something else I want to clarify, it's going to become logistic wise. Okay. I call the axial stress here sigma ZZ because it's drawn parallel to the Z axis. There is some people who, for their cylindrical coordinate system, including me as well, sometimes they use R theta and not Z. They use R theta and X, R theta and Y. Then your axial becomes sigma XX or sigma YY. We do that when we are dealing with horizontal wells or horizontal tunnels. So Nassim, for instance, assumes that my graduate student Nassim, he has a horizontal well drawn parallel to the x-axis. So if you read his papers, the axial stress would be sigma XX. Okay, it's understandable. Hakim, who else? Hakim is using vertical wells, so his axial stress is sigma ZZ, right? So when I was in my PhD, I was using horizontal wells, but for some reason I had them parallel to the y-axis, so it was sigma YY. So don't let yourself be confused with that. And I know there is a lot of ways you can get confused outside. It's not your fault. Now, as I mentioned earlier, I'm very, very interested about where the fractures are starting. So when I drill a well and I want to fracture it, right? So I'm gonna put fluid in it and I'm gonna start pumping it at high pressure. Where is the fractures gonna start? They are gonna start at the walls of the borehole, right? The edge of the borehole. So I'm really interested about the stresses on the wellbore walls, okay? Which is basically here. We say at, what did I do here? At, this is R equals RW, okay? Or sometimes they use small r for RW. They mean the wellbore radius at a distance R equals to the wellbore radius. What I drew before, yeah, it's an R bigger than this R was bigger than RW, right? It was much bigger. Now I'm gonna go exactly at R equals RW, and I will look at the stresses there on the edge of the wellbore. I'm gonna have a radial stress, and I'm gonna draw them in the radial in the tensile direction, just because of I want them to look nice on the plot. That doesn't mean that is. Don't worry about where the arrow is pointing, because that's where, if you calculate a positive value, it's pointing this way. If you calculate a negative value, it's pointing the other way. The way I'm showing you the arrow now is if you have a negative value, that means it's a tensile radial stress, which most likely you are not going to have, but it looks better on the pictures. That's why most of the schematics you find online are going to be showing them like this. This is the tangential stress, also known as hoop stress, sigma theta theta. And then I have the radial, the axial, sigma ZZ. And I want to ask you a question. What is my shear on the wellbore radius? How do I draw it? The answer is I don't have shear stress on the wellbore radius. Shear stress goes to 0 at the wellbore radius. This says sigma r theta at RW is equal to 0. So nice. Any questions? Okay. So this is a schematic. Well, here I use a small RW for the wellbore radius. That's fine. It basically shows both axes, actually. You have the x-axis, y-axis, z-axis as the Cartesian system, coordinate system. And then you have the wellbore is basically you have the empty well, surrounded by the steel casing, which is surrounded by the cement shed, and is surrounded by the rock formation. And you have the cylindrical stresses here and here. Yeah. I was gonna say that now. When I drew this, I wasn't thinking very well. So I showed the radial stress to be in the tensile direction, the axial stress in the compressive direction, and the tangential stress also in the compressive direction. So I really mixed them up. But yeah, where the arrows are pointing is based on the sign in front of what you calculated, basically. And then we have the additional complexity. The rock formation has pore pressure. The wellbore has fluid inside. The fluid is under pressure. We call that wellbore pressure, PW, and so on and so forth. Now, there is a big, long history of calculating those stresses. It's not simple, okay? It's not simple. There is a lot of theory behind it and a lot of history about it. We will start from 1831, sorry. Lamé and Clapeyron. You may know Clapeyron from thermodynamics. Clausius-Clapeyron equation. And Lamé, you already know about Lamé. They were doing calculations for cannons. It was like, I have this cannon. How much can I load the cannon before it explodes? So they tried to calculate the stresses on the walls of the cannon to see how much they can handle. And this problem obviously is analogous to this. For some reason, the expressions they derived, they became known as the Lamé solutions, the Lamé equations for thick-walled cylinders. So they sort of wash out the Clapeyron name, which is sad. But yeah, the Lamé equations is basically the first solution that came to basically for the cylindrical stresses. Now, in the oil and gas industry, we still use those equations for casing integrity, for casing sort of stresses. Because the casing that we use when we run casing inside the well, they are what do we call it? They are basically thick-walled cylinders. So if you did in drilling, we do the von Mises and Lips. That one is basically the Lamé equations. And there, that's confusing, they are using tension as positive, compression as negative. So if you use the drilling book, it will be very confusing compared with the geomechanics book. And it was confusing for me. Last year, I was teaching both of those classes, and I have to use tension as positive in the one class and tension as negative in another class. Anyway, that's what Lamé and Clapeyron did in 1831 for cannons. And then later of that century, in the 19th century, Kirsch came, Gustav Kirsch. He was a German mechanical engineering professor who took the Lamé equations and basically applied them to a fully theoretical problem. He said, imagine I have a plate. The plate is, it was something like this. I have a plate, a square plate.
Was 2D, right?
Yeah, certainly 2D. Where is the pen? Oh, there you go. It was a 2D plate like this, and I have a open circle in the middle, and I have a stress here, a stress here, a stress here, and then I think also inside the plate, I have tension on the walls of the plate. And remember, this was a mechanical engineering professor, so it wasn't really about wells. But this looks a lot like I have this stress outside, and then I have this wellbore pressure inside, right? It looked very much like that. And
so it didn't include the pressurized system.
Yeah, pressure on the plate, tension on the plate, not even pressure. The pressure acts like a tension. It tries to make the plate bigger. So we started getting into what we tried to do. Okay. Then there was somebody, I don't know who took this stress outside and he made it like by stress. That means he made the stress on one place bigger than the other. So you have SH max and SH min. Because what Kirsch did was the same stress all around.
Okay.
So just sigma. And he took it and he made it maybe sigma 2 and sigma 1 in a sense. Okay. So we don't know who. I remember my advanced drilling professor, he was saying, I don't know who did it. I tried to find out myself who did it, but I don't know who. And then we will go, okay, there was somebody else. I ignore him in this analysis, but there was somebody called Inglis in 1913. He took those equations and he said, how about we do the same problem as Kirsch, but we have an elliptical opening. So he modified the Kirsch solutions for an elliptical opening. Okay, he did it. It was fairly easy. But we will ignore him for now. Inglis becomes very, very important in the fracture modeling, actually, because the way the fracture propagates is it's elliptical, right? And it has fluid inside it. So they use it. If you talk to Mark McClure of Resfrac, he's using Inglis equation for the fracture propagation model. No, it's part of his model, basically. Because, you know, it's like a semi-ellipsoid, right? So it goes like this. It looks like the stresses, yeah, for the fracture, yeah.
For the wellbore.
No, we use it for, Nassim uses it for the wellbore. I use it for tunnels. Yeah. Inglis is like the modification is basically Kirsch equation with some factor for a different height and different width for the wellbore. Very, very easy to adapt it. I'm just saying that it's there just to know about it. But then we are gonna go 59 years later after Kirsch. And that's the first geologist who put their hands on these equations. That was Hubbard and Willis. And we talked about their paper. Is very, 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 probably the best paper in One Petro, they say, which is One Petro is the website of the Society of Petroleum Engineers. It has papers from 1924 in it, or 1913, I think. Because SP started as it was AIME, American Institute of Metallurgical, Mining, and Mechanical something engineers, and they had an SPA, and they had in 1913, they made a Office for Petroleum Engineering. And then in 1957, this Office for Petroleum Engineering became branded as a Society of Petroleum Engineers, October 6, 1957. And then that's when SP started, but SP was part of AIME. And then in 1985, SP broke up completely and became completely independent of AIME. That's why when you read Hubbard and Willis' paper, it's gonna say AIME paper. But anyway, I showed you that paper in class. Basically, what did Hubbard do is that he took the Kirsch solution for, and who knows, it might be Hubbard who did the who did the two different stresses. I don't know. He said, okay, we have wellbore pressure, By the way, it's not elliptical. It should be perfect circle. Now, we sort of ignore English. I have wellbore pressure. And I have two stresses by how do you say? By something stress loading. So I have SH max, SH min, SH max, SH min, SH max, SH min. I have wellbore pressure. And now he also added pore pressure. Pore pressure. But he added pore pressure as a static loading. Very, very like fixed value of pore pressure. Just like we do in the homeworks and everything. PP. So he added this complexity to it. And maybe he also made the one stress loading to two stress loading. It's a 2D analysis, okay? And it was he used those equations to tell people that you no longer have, it's not always, fractions are not only horizontal, only vertical. He said there could be either vertical or horizontal, and use these equations to decide if they are gonna be horizontal or vertical. And it was an excellent paper. And then 10 years after, you have Himson and Fairhurst. Himson is still, Himson. Bezalel Himson is still alive, I believe. And if you go to the ARMA conference in the summer, happens around June every summer, you are gonna see him. You most likely will see him. I think I saw him in New York, 2019. He's like 85 years old. Himson. Yeah. University of Minnesota, actually. If you know, University of Minnesota has a very well-known rock mechanics lab. And the rock mechanics lab has people from civil engineering, chemical engineering, mechanical engineering working in there. It is so big. I think these are the ones who started it. Charles Fairhurst, I think he was the professor, and Himson was the student. I don't know. I think it was after one of them graduated, he became a professor at Wisconsin, I believe, and that would be Himson. I think Himson was like, I want to say, I read the bio somewhere. It said that he was born in the 1840s, which says that he was 27 when he came up with this. So he took the equations of Hubbard and Willis and basically incorporated poroelasticity. So it made the poles to change size. So that Biot's poroelastic coefficient alpha B, he incorporated it into these equations. So this is what they did. Himson and Fairhurst. And this is as good as we can get, pretty much. There is some more complicated models we can use that are around, but for classroom purposes, these are basically, oh, okay, 3:15, we have 5 minutes. These are basically as complicated as you can get. Hakim, in his work, is using Himson and Fairhurst. Well, not completely. Because Himson and Fairhurst, what they did it only for the radial and the tangential stress. They didn't do it for the axial stress. I don't know who did it for the axial stress. But there was a guy, he's the vice president of Liberty. His name is Lynn Wire. He came over to give us a presentation last year. In his thesis, he has an appendix at the back. He got his PhD from Delft. He's a Dutch guy. And after that, he moved to San Francisco. He wrote fractal modeling in the 90s. He wrote Fractal, actually. He helped write Fractal. In the back of, he has an appendix where he shows all the equations for this sort of modification for proelasticity. So for us, in this class, I will only get you up to up to Hubbard and Willis. This is as deep as we are gonna get. We do see these equations in the next class briefly. But really, if you know how to use the Hubbard and Willis, we will be good to go, basically. This is as deep as we can get for the time that we have available and stuff. So, very quickly, let's see the stresses for a vertical well. Okay, I have a vertical well. It's a vertical well, so it's drilled parallel to SV, okay? Let us take angle theta, being a clockwise angle from SH max. So it's basically.
The theta equals 0 is aligned with SH.
Exactly. It's basically what I have here. Let me draw it very quickly. I have this SH max, SH mid, SH max, SH mid. Okay, so my theta is taken from here. So if my radius is here, this is theta, right? This is my theta angle. So how do I calculate those stresses? This is how I calculate the radial stress, long ugly equation. Now, but before being scared, think about, we're gonna do it later, but there are ways you can simplify this. But it's fairly easy. I mean, if you know the values,
yes,
just plug them in and get them. Unit R, RW, SH max, SH min, PP, PW, PP, and theta. And then you find the value of sigma R. This is how you find sigma theta theta. And this is how you find sigma ZZ. How does it look?
it's not complicated.
Yeah, but it's not your first time looking
when
at
you
it.
get used to it, it's pretty easy, especially when you have all the numbers.
Yeah.
Yeah.
So some things I want you to notice. Okay. CSV appears only the axial. Oh, I don't want to show the shear stress. SV appears only here. You have SH max and SH min in the other two. You have 2 theta, you never have theta. Correct. Yeah. Thank you, Hakeem. I forgot about it. And now let me show you the equation for the shear stress. Very, very similar to the rest, but now you have sine theta, sine 2 theta. That's fine. But I want to ask you something. Imagine, what if I do it at R equals RW? We use small r here. Okay, small r for RW. Okay. This will become 1. This will become 1. So I have 1 plus 2 minus 3.
It'll be 3 minus 3 is 0.
Yeah, 3 minus 3 is 0. So sigma r theta,
And R equals RW.
yep, is 0. That's why I said earlier, shear stress goes to 0 on the wellbore walls. So you can see it now. Right?
Also for theta equals 0, it means R theta at SH max is 0 too. For orientation,
No, it would be PW minus PP times this.
no, for R theta.
R theta.
Yeah, the shear.
Oh, the shear.
Yes.
Yeah. There are several ways you can get
So it should be increasing towards 90 degree. That's its maximum. Its
Yeah.
minimum is,
yeah. That's true. That's true.
its minimum is
Because theta equals 0 is
yeah, its minimum is it's 0 plus P. Yeah, 0 and P. That's the minimum.
yeah.
So it's KP.
So 0 and 180 degrees up and down.
Yeah, it means 0 means KP.
Yeah.
Yeah.
Yeah, that's true.
Like 0, 1, P2, P3, P4.
Yep. So now imagine something. And this is an important thing to understand. And this is the last slide we're gonna see today. Okay, imagine these equations, and I calculate them for RW is constant. R can vary. I calculate it for R increasing R. What do you think is gonna happen as the R increases? If the R increases, let me help you think here. R is in the denominator. What is in the numerator is constant. This is constant. If this increases, this becomes 0. 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 This becomes 0, but I don't really care about that. Yeah.
So
Yeah, of course. Yeah, you're right. You're right. So what happens now is that something that you are gonna see better in the next slide.
which is the spaces in the parking.
Yeah. If linear wellbore stresses become closer, they become closer to the far field stresses, the further away you get from the well. That means if the well is here and I measure the stresses here, here, at some point here, I'm back to SV, SH max, and SH min. So the tangential stress would be either SH max or SH min. The axial stress would be SV. The radial stress would be the other, the third one.
So the shape of R will becomes a square.
Yeah.
At that time.
Yeah. The shape becomes basically, yeah, exactly. So for a vertical wells at theta equals 0, as I go away from the well, sigma Z becomes sigma V, sigma R becomes sigma H max, and sigma theta becomes sigma H min. And that is easier understood. Imagine if I draw something here. Imagine if I draw the well. I make it small intentionally. I have what? I have SH max. You might not be able to see it because of the camera. I have SH max here. And then I have SH min, SH min. Okay. Okay, imagine if I'm at theta equals 0. So I'm basically here, far away from the well. Okay. It's not easy to, let me draw it downstairs. Okay, this is my well. This is my SH mean. This is my SH max. This is my SH mean. And then I have another SH max here. Now, somebody's asking me, I have PW here. I want the stresses here, okay? Or here. It's far away from the well, okay? Try to draw the stresses in the direction here. The radial stress will look like this, right? The tangential stress will look like this. The axial stress will look like this. I don't care about the shear stress for now. Okay. Now, look, the green is in the direction of SH max, but here is somebody else's work. So they didn't use my own color scheme, which I was using when I was a PhD student. I kept it going. Basically, this is radial. The grid, right? Look at the hoop stress. It's in the direction of SH mean, right? So the hoop stress becomes eventually equal to the sigma H mean.
But also the graph is for theta equals 0.
Yes, this graph is for theta equals 0. Yeah. I have the other one coming later. And then, yeah. This. So you see, as I go, yeah, as R over RW increases, this value increases, moving to the right. I get to a point where basically after this A, imagine A being here, and B being here, I get to a point where yeah, and now I have the radial stress becoming sigma H max, the axial stress, sorry, the tangential stress becomes sigma H mean, and look, the old sigma H mean with capital H, and then the other one becomes the axial stress. And now very quickly, imagine now theta equals 90. Okay, let me draw it very quickly so that we save time. I hope there is no class waiting, but if they do, they can wait. This is important stuff. SH max, SH mean, SH mean. Now I'm here. I want the stresses here. And I will draw them. Look at the arrow. The radial stress is like this. The tangential stress is like this. I made a mess. Sorry. And the axial stress is like this. Okay. The green arrow for the radial stress is parallel to SH mean, I think. Yeah. So this is basically green. Sigma H mean. Yeah. Oh yeah. And the theta would be the red one, and the blue would be the ZZ. Yeah. Anyway, thank you very much. I will see you on Wednesday.